If f is integrable on closed interval ab and the integration from a to x ft dt is equal to 0 for all x belonging to this closed interval ab, then ft equal to 0. For all x belonging to this closed interval ab, then this ft itself is 0. This we need to show almost everywhere. This a dot e dot means almost everywhere in this closed interval ab, right? So it is given to us that f is integrable, small f is integrable. Let's suppose that, if possible, suppose f of x is strictly positive on this set E, having the measure positive, strictly positive. This is a set E and the measure of set E is strictly positive. So if possible, suppose fx is positive on a set E of positive measure. Positive measure means that its size is greater than 0. Defined by the specific measure, its size is greater than 0, right? Then there exists a closed set, let's say F, where F is a subset of E, right? E is having the measure positive. So F is also having the measure positive. So let's write this. Then there exists a closed set F, which is a subset of E, with measure F to be strictly positive. Now if from the open interval AB, what is given to us that f is integrable on closed interval AB and this integration is 0 for all x belonging to AB. Now this integration is from a to x, right? So if I consider an open interval AB from which I subtract this closed set F, whatever set I get, let me name that set to be O. Is this O open or closed? What do you think? Is this set O is open or closed? Yes. This is your open interval. This is your closed set, right? Suppose I take AB to be the value of AB to be, let's say, 0, 1, right? And let me take the closed set to be like 0.25 and 0.75. Suppose these are the endpoints. So what I get this to be the union of 0 to 0.25 union 0.25 to 0.75. So I will be getting the union of open sets, right? So whenever we remove a closed set from the open set, we are getting the open set. The union of open sets. The union of open sets is itself open, right? So this O is your open set. So let's take this O to be an interval from which F is removed. So we can also take O to be the disjoint union of the collection of open sets, a countable collection A and B n of open intervals, right? Please remember this. Now this F is strictly positive on the set E, right? So the integration for this F from A to B can be equal to 0 or cannot be equal to 0. It can be equal to 0 or it cannot be equal to 0, right? So if F is positive, then either the integration of f from a to b is non-zero or else it is 0, right? Okay, if it is 0, then what happens? 0 is equal to the integration from a to b f. that is equal to, now this interval AB is what? We have written that O is the open interval AB minus the closed set F, right? What is AB then? It is the set O plus F. So can I write this F to be the integration over F plus the integration over O? The interval AB is the union of the set O and F. Okay? Alright. So this implies this 0 is equal to the integration of F over F plus the integration of F over O, which further implies that the integration of F over O is equal to the negative of integration of F over F, capital F. And this integration is non-zero. Why? Because this is the integration over F, and F is of measure strictly positive, and small f is also positive. We have taken F to be positive on the set E, having the measure E to be positive. So that is why this integration is non-zero. And what is O? It is the union of the disjoint collection of open intervals, the countable collection A and Bn of open intervals. So we can write further the integration F over O to be equal to, therefore it is equal to the summation of the integration of F from An to Bn. Yes? And this integration is because non-zero from this, from 1. So this implies the summation of integration of F from An to Bn is non-zero. That is the sum of the integration of F from A1 to B1, then integration of F from A2 to B2 up to so on is equal to 0. Now here n is denoting 1, 2 up to so on. Can I write that from this sum? Can I write that for specific value of n, for some value of n, the integration of f for that specific n, this integration is 0? Yes? Okay. So thus, because this summation of this integration is non-zero, thus for some value of n, the integration of f from An to Bn is non-zero. Yes? In the next step, I would like to break this integration from An to A and from A to Bn. I have break this integration at the point A. I have taken the sum of these two integrations. I would be like to take the sum of these two integrations for this point A. So the integration of f from An to Bn is non-zero implies the integration from An to A of f plus the integration from A to Bn of f is non-zero. When the sum of the integrations is non-zero, this implies what? This integration is also non-zero. Either of these two integrations is non-zero. This can also be non-zero, or the integration from A to Bn of f is non-zero. Means either of these two integrations is non-zero. So writing this implies either integration from An to A f is non-zero, or the integration from A to Bn of f is non-zero. If I interchange this limit, the sign would be changed. If I write this from A to An, this will be negative of f. And now if I multiply both the sides with the minus sign, again I get the integration from A to An f is non-zero. So in either of these two cases, we see that f is positive on set of positive measure. Yes? So writing this, In any case, we see that f is positive on a set of positive measure. Then for some x belonging to the closed interval AB, we have what we have here, the integration from a to an of f is non-zero, right? This an is for some value of n, and this an belongs to the closed interval AB, right? So can I write that for x belonging to this closed interval AB, we have the integration from a to x, the lower limit is a, right? Upper is an. So here also lower limit should be a and upper is x, the point which is belonging to this closed interval AB. So we have the integration from a to x of f to be non-zero, which is a contradiction. What is given to us? It is given that if f is integrable on closed interval AB and integration from a to x ft dt is 0. From a to x the integration of ft dt is 0. Here we have shown that the integration of a to x f is non-zero, but it is given that it is equal to 0 for all x belonging to the closed interval AB, right? So which is a contradiction. So our supposition was wrong. We have taken for the case of f to be positive. Similarly, we can also take the case where f is negative. Then also we can show that this integration is non-zero for both the cases, right? So similarly, for f negative on a set of positive measure, we can show that there exists x belonging to the closed interval AB such that the integration from a to x of f is non-zero. So this is a contradiction. For f positive and also for f to be negative, we can show this, which is a contradiction because it is given that this integration is 0. So therefore our supposition was wrong. What we need to show that this f is 0 almost everywhere, and we have supposed f to be positive or negative, right? So this supposition was wrong. So therefore, hence this f should be 0. So hence ft is 0 almost everywhere in closed interval AB. I hope this proof is very clear to you. Yes? Okay, thank you. Stay blessed.